Hello?
Hey, Zed.
Yeah, can you hear me?
Yeah, I can hear you.
Okay, cool. This is so bizarre. I've never done this before. Okay,
Yep.
so I typed, so I figured it out and I typed in the code that it gave me.
Okay.
It basically, here, let's see. It basically so after I
Hello? Yeah, I can hear you. Go ahead.
yeah, can you hear me?
Yeah, I can hear you.
Okay, hold on.
This is so bizarre. I've never done this before.
Wait, okay, wait, hold on.
Hold on. I'm muted now. So go ahead
Okay.
now. Yeah.
Okay, so when I ran it, it gave me here. Can I share? How do I share my screen with you?
If you go on the bottom, there will be like a green button which says share
Oh,
screen.
okay. Okay. Can you see anything?
I can see you. I can see your screen. Yeah.
Okay. So yeah, so that's what I got when I ran it. But then I do this
Mm-hmm.
knit document, and this comes up. Or if I want to do it via here, PDF, that would come up.
Oh, I see. Let's see. Okay. Can you go to the? Can you scroll to the bottom of your document? Uh-huh. Okay, that looks fine. Okay, this is fine. Just send me the RMD document. I'll take care of the rest.
Okay, I sent the RMD, but can you open it? The one I sent
I
you?
can open it. Yeah, just send me the updated one.
Okay, cool. Sounds
Yeah.
good.
Yeah.
Thank you.
Yeah. Thank you. Okay, maybe you want to stop sharing your screen now.
How do I do that?
If you if you go to the bottom, it will have an option stop, or on the top you'll see something like stop sharing, like a red button. Yeah.
Okay. Thank you.
Yeah.
Second, were they cleaning this thing or?
All right, so we'll get started. This is going to be a different session because first time doing it. Is everyone able to hear me? I hope. Okay, you can. Okay, I was going to assume. Okay, let's see. Yes, okay, that sounds good. So we'll get started. Before we get started, I know this is a new thing, so embracing change is part of life. So let's just try this out and see how this goes. So what I'm going to do is I'm going to share my screen and you'll be able to see as I write, you'll have my notes, access to my notes, and you'll have access to whatever I write after the end of the session. Let me first go ahead and share my screen. I'm going to write here. The discussion material is already available on Blackboard. So if you go on Blackboard on discussion 9, the problem set is already available there. So I would advise that you go ahead, download it, have it open somewhere because we need access to the problems. So there are two problems here, and I'm going to take both of them. Before we get started, since the project is due tomorrow, I just had a quick uh, thing that I wanted to talk about, and that was essentially problem 12. So number 12 in your, this is your project. So your project essentially requires you to predict, to actually come up with a problem. And when you come up with a problem, if you're doing a test, before you're doing a test, one thing that you really need to verify that if you're doing a t-test, you need to check, is it a simple random sample and is the normality condition satisfied? Okay, and the way to do that is generally QQ plot. Okay, now if this condition of normality is not satisfied, essentially just applying t-test is not really going to be useful, or the results that you get out of, you will get a result. If you do a t-dot test, you'll definitely get a result, but you cannot really trust onto what the results are, right? So if your QQ plot fails, right, then you will do a Wilcoxon test. Okay. And the reason for that is because the assumptions of normality are not satisfied, and so we cannot simply apply the t-test, and hence we should go on a different approach. This testing strategy would change and evolve as we go along the class. So we'll study more tests, but for this project specifically, this is kind of the workflow that you need to follow. So check for simple random sample, check for normality. If that's satisfied, your t-test is okay. If not, then we go to doing a Wilcoxon test. Okay. All right. So that was about the project. It's due tomorrow, so hopefully everyone has it ready. If you are facing any issues converting into PDF, please feel free to email me. If you are facing any issues, I'll happy to talk about the discussion. Okay, just feel free to email me and we can set up a convenient time to talk. Okay, I hope everyone has their handouts ready. So we'll start off with problem 1. So this is essentially a continuation of what we did last week. We are given two groups of vitamin C and placebo, and we are asked if in this time we're explicitly given that we are not interested if vitamin C can actually increase the duration of the cold. So what this essentially means is the vitamin C is supposed to, this is our expectation, that it's supposed to decrease the length of the duration of the cold. Okay, so what should our null be? So our null will be, there is no effect because of vitamin C. And when I say no effect, that means it's no effect on the duration of the cold. This essentially translates to, in mathematical terms, that mu1 is equal to mu2. Or alternate, on the other hand, is vitamin C decreases the length of cold. Okay, and this essentially translates to mu1 less than mu2. Okay, if you have any questions, I've also shared a document with you, a Google document. If you don't want to ask it on the chat, you're welcome to ask it on the document, and I'll try to go over it before I end the discussion. The link to document is on Blackboard. So if you have any questions, I'll take them at the end of the discussion. Okay, so that was what the first problem asked us to do. Let's go on to problem 2. So problem 2 is asking us to construct a 95% confidence interval for the difference in population means. And the next question that it asks is, does the confidence interval support the alternative hypothesis? Okay, so whenever we generally talk about the 95% confidence interval, so in this problem, it's not clearly specified as to what this 95% confidence interval is going to be, okay? So when it's not specified, we go with the non-directed version of it, okay? So we assume that the alternate is non-directional, okay? And by this time, you probably know the formula for that. So the formula for the non-directional version of this hypothesis is this. Right. Things get a slightly tricky if you're asked the upper or the lower confidence interval, but we are going to work with the non-directional alternative, which is essentially, which has both the form of what you see here. If it's non-directional, if it's directional, then either of the ends is minus infinity or plus infinity, but we'll not worry about that right now. So we know this. And in order to simplify, we are also already given the value of 0.025, and this is minus 2.08. And you're also given the value of standard error, which is equal to 0.254. Okay. So the way we got the standard error was very simple. Sorry, this is actually 0.35. Okay, so the standard error, the way we got is what we did in our previous class. This is essentially equal to your summation of SD square and 1 and SD square and 2. Okay, so next what we are essentially asked to do is we are asked to plug in the values. So what we'll do is plug in the values, and if you plug in the values to the above formula, you'll get the interval to be lying in this range. Now, what this essentially means is if you look it up on the number line, your 0 is here, the lower value is here, and the upper value is at 0.05. So one thing that you will notice is this 0 is contained in this confidence interval, okay? And whenever that happens, what essentially this is trying to tell us is there is some probability of 0 being included in this confidence interval. And what we were testing initially was what is this equal to, right? Now, if 0 is part of this confidence interval, this essentially means that it's likely that this difference between the two groups is going to be, there is a possibility that this can also be 0. So 0 is included in 95% CI. And that essentially means that the effect, it's quite likely that we'll not be able to reject the alternate. Okay, sorry, failed to reject the null. Okay, so 0 is already included. There's a likelihood of 0 being included as part of your confidence interval. As the 0 is already included in your confidence interval, so there's a likelihood of it not being, because of this, you'll not be able to reject your null. Okay. Okay. Are there any questions at this point? Feel free to put this on chat. Let me quickly also check on the document. Okay. So if there are no questions, I'll proceed. Okay. So in third part of the problem, you're given an output of your t-test. So assume you're doing this on your computer, and your computer outputted your t statistic to be minus 1.9253. Okay, and your p is 0.03. So before we proceed, let's first actually, I wanted to clarify one thing, and that is very confusing in a lot of it's confusing to a lot of students. Okay, so your t statistic is minus 1.9. Remember, your null was mu1 equal to mu2, and your alternate was mu1 is less than mu2. Okay, so the moment you see this alternate, your t statistic, which is defined by y1 minus y2 divided by the standard error, you expect this to be negative, okay, which happens to be true in our case. Okay, now let's take an example. So this is an aside question. What if your, so this is a separate, let me mark this in red. So given okay, so assume this is a given question. Okay, so how do we go about this? We are not given any information at all. You're only given that the null distribution, the null was mu1 equal to mu2. You're given the alternate as mu1 less than mu2, and your t statistic is given to be 1.952. Okay, so how does it actually look like? So if you again draw your t distribution curve, your t statistic happens to be here, but your alternate was mu1 less than mu2. Okay, now let's recall what the definition of p-value is. So the definition of p-value is the probability of observing a t statistic as extreme or greater than what you're observing. Okay, in this case, this is how the extreme is going to get defined. So your alternate says that mu1 should be less than mu2, and hence the only interesting direction that I'm interested in is below this particular value. Okay, now if that's below this particular value, then the area that I'm interested in is this shaded area, and this value at the middle is 0. What this essentially means is that your p-value for all reasons is definitely going to be greater than 0.5, right? Because you already have half of the area included. So whenever you come across any directional hypothesis, the first thing that you should check, so check if H alternate and T statistic have compatible signs. And how do we check for compatibility? So if mu1 is less than mu2, we expect T statistic to be less than 0. And if mu1 is greater than mu2, we expect T statistic to be greater than 0. If this is not the case, then you don't need any table to actually calculate the p-values, right? So for corresponding cases, let's take this case, if your mu1 is less than mu2, and you see that the t statistic is opposite, that means it's greater than 0, then you can stop right there and say that there's no point proceeding. The p-value is definitely going to be greater than 0.5. Okay, so that was an aside. Let's go back to our original problem 3. Okay, so your p-value is 0.03, and we are asked what is the interpretation of p-value here. Okay, so what this essentially means here in this particular case is we already know the definition of p-value, but we can be a bit more specific in this particular case. And the reason we can be a bit more specific is because our alternate is directional. Okay, so this is what I would write it as. It's the probability of observing a t statistic of minus 1.9253 or lesser, And this part, both of these parts are important, or lesser. Why did I say or lesser? The reason to say or lesser is because the only interesting direction that I have is mu1 less than mu2, okay? And one more important thing, a lot of you are still doing it wrong, is this part about the assumption of the null being true, okay? Okay. Okay, so this part is important. So the probability is only based on this assumption that the null holds, okay? So that the second part of this statement is very important. Okay, so that was what was asked in problem 3. It was a very simple problem. It's just there to give you a sense of what exactly does the interpretation of p-value is. We'll go on to problem 4, which is a continuation of this problem. And you're given in this case, your alpha is 0.01. You know that your p-value is 0.03, okay? Now, why do we reject, right? So what would happen? So the first thing that you see is p is greater than alpha. Now, what this essentially means physically is you're given this particular distribution. This is your null. So assume that your distribution was being followed by both the groups. Before you started the experiment, you said that this is my threshold level of T alpha. So if anything falls in this region or below, I mean on this, right, on this side, then I'm going to say that, or this is for, okay, let me be consistent because we are working with mu1 less than mu2. So what we were essentially saying is if anything falls in this region on the left half, that is anything which is less than T alpha, then I'm going to say that the value does not, the probability of that happening is very small, and hence I can say that my assumption does not hold. So if your p-value here, the p-value that you're getting here is greater than alpha, what this essentially means is you're falling actually in this region. Okay, so your T statistic is somewhere here, which is well beyond your what you define your threshold to be, and hence we can say, observing all this, that we fail to reject. Okay. Okay. So any questions at this point? Okay. And the only reason we're doing this is because your alpha was set to 0.01. Now, if alpha was set to 0.05, that would mean that this is alpha equal to 0.01. And if your alpha was 0.05, the result would change. Okay. All right. Okay, so let's proceed to problem 5. And this is again a very simple problem. The problem is asking what the effect size is. Okay, and effect size is an important concept. Effect size essentially involves you to look at the mean differences between the two groups. So if you notice your example of when you worked with the spray example in your previous homework, if you look up the solutions, I've also done one exploratory analysis. So this was your spray A. This was your spray B. And somewhere here was your spray C. Okay. This is an aside, so I'll separate this out. So just looking at the data, it's kind of difficult to judge whether there is a statistically significant difference between A and B or not. We can kind of be sure about the difference existing between A and C or B and C. But the reason the difference between A and B is tricky is because there is a lot of variance that happens in both these data sets. Okay. And why is there a lot of variance? Because you can see the branches, the whiskers are pretty long. So one way to actually kind of adjust for that effect, that I want to look at the differences between these two groups, But in some sense, I also want to account for the different variances that exist in these groups. So effect size in some sense captures that effect. It's a dimensionless quantity. There are no dimensions to it. Okay, it has no units. You're essentially looking at a division of numbers that have the same value, that have the same units, so the units get canceled. So in some sense, the effect size between A and B in this case will tell you how much difference actually exists between A and B, having accounted for the different variances in these two groups. And you can do the same thing for C, okay? Why is this number important? Is this number is essentially capturing this information about how much variance actually exists. If I were to remove this, just looking at the mean difference, you would say that maybe A and B are different. But if you do this example, and if you look at the effect sizes are not really large, okay? So if they're not large, that's basically generally because you've accounted for the difference. So if this denominator, the standard error of the differences is high, the effect size essentially reduces, okay? And that's essentially telling you that there is difference between the mean of the groups, but if you account for the variance, that effect in some sense actually disappears. So if you did a t-test or a Wilcoxon test in between A and B, you would notice that the p-value is around, I think, 0.5 or 0.6. It doesn't turn out to be significant. Even though if you plot the box plot, you'll see that there is a difference. The reason you don't see this is there is a the p-value is not significant is because there is a lot of variance between both the groups. And hence the difference that you see is, we cannot really say that this is not happening by chance. So the difference that you're seeing could have just arisen because of chance. Okay, so that was a motivation of why the effect size is kind of important. Nothing really great about doing the calculation here. It's a very simple calculation, or you already have all the numbers. And if you plug in the values, I think you get 0.765. Okay. Now let's take problem 6, which is an interesting and a slightly, not exactly, but it's a slightly challenging problem because it just makes you think as to what really is going wrong. So imagine you just carried out this particular study in 100 test centers. Your alpha was set to 0.01. Only one center ended up rejecting the null. Okay, if you remember in our previous case, we failed to reject it, right? So our alpha was set to 0.01, our p-value was 0.03, we failed to reject. Now we go back to our problem 6. We have 100 test centers, 99, excuse me, 99 of them failed to reject. And only one of them is rejecting. So what's going on? What's so special about what this one center? Anyone wants to, I know most of you are muted, but anyone wants to take a guess? By the way, if you want to unmute yourself, there's a button on the left which has a mic. Feel free to unmute yourself if you want to say what you think is going on. Okay, anyone? We'll try one more time. Okay, so what really is happening, right? So there's nothing really special actually about this one center. The only reason it's rejecting is actually just by chance. And the way to see that is you had 100 test centers. Now, when you test based on a value of alpha, which is set to 0.01, in each of one try, so let me do it step by step. So probability of making a false positive claim in one trial is equal to alpha, which is equal to 0.01. Okay, I'll just quickly go through why this is the case. So when you decide what your alpha is going to be, let's take the case of only a directed hypothesis. So your alpha, your alpha is set to here. So what essentially am I saying? I'm saying that when I do that, when I put this through a hypothesis test, and this is my curve, and I see anything following in this extreme, then I'll say that, this is not a likely event because the chances of this happening are very small. In our case, this is set to 0.01. So if anything that happens in this tail is not satisfying our null hypothesis, and hence we reject the null. However, if you also notice that the chance of anything, if the null was really true, okay, so if H naught is actually true, okay, then there is a chance then you're creating an error. Okay, you're creating a false positive error if you reject the null. Okay, and why am I rejecting the null? Because I'm saying that my data actually falls somewhere, let's say here. Okay, so if the data point happens to fall here, you're going to reject the null, but it's actually really happening. There's actually a very small probability of this happening, but there's still a possibility. And hence you're actually rejecting the null in a false positive way. It's called a false positive because the null is actually true, but you're saying that it's not true. So there's a one term. So this is the terminology of claiming it to be a false positive. So you have a probability of 0.01 in one trial of doing that. Now, what you're doing is you're testing for multiple hypotheses. Okay, so if you have 100 hypotheses, you have 100 times 0.01 ways of making this false positive, and that is equal to 1, right? So at least one of the hypotheses that you're testing is you're definitely going to reject it. That's just the way your testing methodology is set. That's just how the hypothesis testing works. Okay, so you expect to make one number of false positives among these 100. So there's nothing special about that one particular center. It's just happening by chance. Okay. Any questions? Probably not, but please feel free to ask. Okay. All right. So we'll move to problem 2. And problem 2 is an example of what we are doing essentially in the class as it's a very simple problem about doing a Wilcoxon Mann-Whitney test. Okay, but before we go there, I'll again reiterate why we are doing all this, right? So you're given two groups. You're given group 1, this is control, you're given group 2, so why? So the reason you're doing this is because they are given two groups and you're asked, is C equal to T? Okay. Sorry, I keep pressing this. So is C equal to T? This is the question that we are really interested in. And what is the answer to that question? So one strategy would have been to do, how do we test this? How do we really go about testing if C is really equal to T? So the best strategy in most cases is just randomize. Or it's also called permutation. What this essentially means is forget about what these labels are. If you have 1, 2, 3 entries and 1, 2, 3, 4 entries, you can do this in 7 choose 3 ways. What am I doing actually? So what I'm doing is I'm saying that there are 7 numbers. I will forget about what labels they have and I'll partition them into 2 groups in 7 choose 3 ways and then see if there is really any difference between these 2 groups that I come up with. So when I do this randomization, I'll test for the mean difference between these two groups and say that how many times can I see a difference which is as extreme as what I initially started off with. Okay. The problem, however, with this approach is it's okay to do so. And what's the problem? So the problem with this is that it's computationally hard, right? You can't keep doing this. Okay, 1 second, we have chat. Okay, so why are we doing C equal to T, right? So why are we doing this? So we are interested in this fact that you're given these two groups and somebody's asking you that, is there a particular effect that's happening because of the treatment? This is again an example picked up from clinical world, but you can think of this in any context. So you can in fact think of this hypothesis that the Wednesday section heights are different from, let's say, the Monday section heights. That's my hypothesis that I'm giving you, and I want to really test this. So we want to test if there is any particular effect coming because of one group. So that's our interest of question, and we want to be able to test this. So one strategy would have been to randomize these labels on these observations and then see that if I randomly partition people in Monday section into the Wednesday section and vice versa, do I see a mean difference in the heights, which is as extreme as I saw originally in my Monday and Wednesday section when I actually permute the labels? That's the strategy that you would use in general to test, right? Does that answer your question, Simrandeep? Okay, let's see. Yeah, okay. So, but we can't do this, right? We can't randomize if you have, so think about this example. Think about you had 100 students and you had two groups which had, let's say, 30 and 70 each. So 170, choose 30 ways. Okay, this is not practical. This doesn't seem to be practical at all. So we say that, okay, fine, this is not practical. Let's see if we know certain things about data. So the other strategy is to do a t-test. But if you're doing a t-test, the data needs to be special. The data is special because, first of all, it needs to be a simple random sample. This actually also needs to be satisfied if you're doing randomization. And the second important thing is you should assume that the two groups are following a normal distribution. So it's called a normal approximation. So you're essentially assuming that there is some normality that these two groups are following. And if these two assumptions are satisfied, it gives you this liberty to actually go ahead and not do the randomization, but do the t-test, because we can assume that the data is normally follows the t distribution. So you can use the properties of the data. However, it's not always likely that you will have the assumption of normality satisfied. Okay. This is also called the rank sum test. There are multiple names. It's also called the Wilcoxon-Mann-Whitney test. It's also called the Mann-Whitney test. There are multiple names to the same example. And this is a relaxation. So relax B. Okay. So if you relax the assumption of B, then the only assumption in some sense it needs to satisfy is this data needs to be a simple random sample. Okay, so how should you decide as to what test you're doing? First of all, in real world, you never do two tests. Okay, you decide as to what your data or what assumption your data is following, and then you decide as to whether it's going to be a t-test or Wilcoxon test or any other test. It will never happen that you will choose both these tests and then see that, okay, fine, Wilcoxon test is giving me significance, so let me just pick up this test. That's a bad strategy. Nobody does that. It's not recommended, and nobody should do it. So in some sense, Wilcoxon is a relaxed way of testing things, right? So even if you do not really test any assumptions about your data and you apply a Wilcoxon test, in most cases, you are going to be pretty robust in terms of the results that you get, which is not necessarily true for t-test. Okay, and that's the reason the question number 12 exists in your project, that you need to figure out if you're proposing your own question, how do you think about what the data really looks like? Does it really follow a normal distribution, or is it a sample random sample? Now, if it's a sample random sample, that's very hard to check, but the only assumption that we can check is the normal approximation assumption satisfied or not. Okay, and the reason it would not be satisfied in our particular example that I've chosen here is because it's coming from counts data, and counts data with a very small number of observations that often will not satisfy the assumptions of normality. So what is it that you're given? You're given a placebo and you're given a new drug. You're given how many number of, what happens to the number of days associated with this particular treatment. And this particular treatment is the shortness of breath. Okay. So you're asked, so you're given the data about how many number of episodes of shortness of breath do you see after new drug, and we expect the new drug to, in some sense, actually decrease it, right? Otherwise, why use it at all? So you're given this particular data. I'm going to sort the numbers that you see there, and the reason to do that is because what we are going to do next. So this is what the data looks like in a sorted form. Now we are asked, what is it that we are interested in? So we are interested in, the first question essentially asks you, what's your null? So your null is mu1 equal to mu2. I'm going to call this my 1 and this my 2. And the alternate is your mu1 is greater than mu2. Okay. This is equivalent to saying mu2 less than mu1. The new drug is essentially reducing your shortness of breath. That's your alternate that you're interested in. Okay, so that was essentially problem number 1 coming from this. So how do we actually go about testing this? Okay, so one thing that you would notice is normality does not hold. Why? Because it's counts data, which is known to follow a Poisson distribution. So what will be our strategy? We'll use a Wilcoxon. Okay, so we're going to use a Wilcoxon test. That's because our normality assumption is not satisfied. So how do we do that? So in order to do that, I'm going to reuse this figure. The way, in some sense, essentially the idea behind this Wilcoxon test is you're essentially looking at the rank information. Okay, and in that rank information can be captured by counting for each observation. Let's say if I pick up this observation, I'm going to see for the new drug, how many of observations are below this particular value. And when you do that, you are essentially in some sense capturing whether there is relative difference in the ranking of things that you see in one particular group as compared to the other thing, right? Okay, and that's another reason it's called a rank sum test, which is what this is called. Okay, so let's see, let me give you an example and then I'll clarify how that works. So the column that you need here is the number of placebo. In this case, it'd be the number of new drug, lesser. Okay, and I'll explain what that lesser means. And on the analog of this is number of placebo, lesser. Okay, so let's see how we go about it. So we go to the first observation. So I've already sorted it, so it makes my life simple as I go along. So the first observation we see is 4. And next, I'll go to this column, new drug, and I'll count how many number of observations are less than or equal to this. So 1 is, 2 is, 3 is, and 4 is somewhere in between. So I give it a weight of 1, I'll give it a weight of 1, I'll give it a weight of 1. And since 4 and 4 are equal, I'll give it a weight of half. Okay. Now what am I doing? So I'm counting how many number of things in the second column, which is the drug column, are lesser than this value. And then you're going to sum it up. So this is the rank that you're checking, and this is the sum that you're going to do, hence the rank sum test. So the rank sum for 4 is 3.5. How? So 1, 2, 3, 1, 1, 1, which is the summation of this, and 4 is the same value, so half. Okay. Okay, so if that's hopefully clear, we'll do it for 5 now. And when you do it for 5, you'll notice that there are 4 observations. This is less than, this is less than, this is less than, and 4 is less than as well. That'll be 4. Okay. Let's repeat that for 6. it's very simple now because things are sorted. So it makes your life simple. So this is short, this is smaller, this is smaller, this is smaller. And these two values are equal. So I'll give it a value of half. Okay, and this we get 4.5. And the remaining things are very simple, 5 and 5. Okay. And you do the same thing for the placebo column now. So I'll start with 1 and I'll count how many number of observations are lesser than this. This is 0. For 2 also it's 0. For 3 also it's 0. For 4, there is just one observation. So we get 0.5 again, because they are the same value. For 6, we have 2.5. Okay, so because 4 and 5 and 6 is equal, so 2.5. We get 3 here. We get 22 here. What is this equal to? So this values here that I'm writing is the summation of these two values. And the value that I'm writing here is the summation of this. Okay. Now we pick up a statistic. This statistic is maximum of these two values. So maximum of 22 and 3 is 22. One quick check if you're doing it right is the summation of these two values, 22 plus 3 should be equal to n1 times n2, which indeed it is, which is equal to 5 into 5. If you go in the handout, I kind of give you intuition about why this happens. Probably not have time to talk about it here, but let's see how it goes. Okay, so this is your statistic. Just the way you were calculating the t statistic, you have a corresponding u statistic now. Okay, and this is the number called us. Fine. So how do we go about really using this? So the way to do that is, if you want to test out what the significance of this is, you'll go to table 6. Now, one key thing that we really need to understand, which I had warned you in the beginning, was you need to read the header of the table. Okay. Okay. And if you read the header of the table, it says that the p-values are for non-directional alternate. Okay. Now this distinction is important because in table 4, let me write this down in a different. So table 4 was different. Table 4 had this variation. Okay. That means it was by default one-sided. Okay. This is non-directional. So it's by default it's two-sided. Okay, that's a very important distinction. So table 4 by default is one-sided. Table 6 by default is two-sided. Okay, that's very important. Okay, so the way to see that is how do we calculate the t statistic? So if you go to table 6 again, let me go back to our original color. So if you go to table 6, you have a column of n prime. You'll go to the column row which has 5 and 5. This is n and this is n prime. And then you'll look up where exactly is your u statistic. Okay, and this u statistic might not happen to be there in your table. So if you go and look it up on this particular row, start searching for US equal to 23, you'll notice that this value actually does not exist on the table. And then we do what we are good at doing, and that's like taking the average. So this value, if you look up, is corresponding to this interval. Okay. We are not done yet. So hold on. Sorry. Okay, this is our p-value coming from, again, this is coming from table 6. Okay, but the table 6 value is by default non-directional. Okay, so how do we convert it to directional? How do we do this, right? So very simple. So we don't really know what the distribution of u statistic really looks like. but we can take a guess, right? How can it look? So maybe it will look like this, maybe it will look like this, or whatever. It doesn't matter what it looks like, right? What matters is if it's directional, then it needs to have only one value of the curve, like one extreme of the curve. But we want to, what we are given is we are given both the extremes. So how do we get only one of the extremes? Well, just you remove this one extreme and we will assume that things are symmetric. So if things are symmetric, we just take half of your p-value bracket. Okay, so this is your p-value bracket, and your directional p-value bracket is half of 0.032 and 0.095. Okay, so this is still the bracket. It's not the exact p-value. But if we actually calculate the exact p-value by taking, so if I take the average, take average approach, then your p-value for directional hypothesis will be half of 0.032 plus 0.095. Okay, and I think that comes around to be 0.03. Okay, are there any questions? Okay, so the reason we were solving this was because we had alpha equal to 0.05. So if this is your p-value, we reject the null. We have a question, it seems. Let's see. Okay, why did we do the last step? Okay, good question. So let's go back again. Okay, so we have so far the p-value bracket for the non-directional version of things is 0.032, 0.095. Okay, now if I take the average approach, then let me just do it again. So, okay, let me write this, change this, and do it. So far, at this step, we only have the bracket. It's a bracket because 23 appears between these two values. Now I want to calculate. So give me, if I were to ask you what exactly is the p-value, okay? So so if I was doing it for a directional, sorry again. So if I was doing it for non-directional alternate, then I'm given the bracket. I'm given the bracket of 0.032 and 0.095. How do I calculate? So the only thing that I can do is I know that 23, so 23 occurs between 21 and 22 and 24. Right. So if you go and look up your table, that's where you'll find these values, or I think it's 21 and something else. So your best guess is to take an average of this to get your p-values. So if I do that, I'll get 0.06. Okay, this was assuming your thing is non-directional. But we are also asked, can you reject the directional alternative hypothesis? So directional alternative. Now in directional alternative, my bracket to start off with is half of this bracket already. Okay, so I would have half the p-values already. So this will essentially equal to half of 0.032 half plus 0.095 half. Okay, and that translates to 0.03. So you can reject null at alpha equal to 0.05, but you cannot in this case. Okay, and you'll find this very surprising. So I can reject the null in case of, I cannot reject the null in case of the non-directional version, but I can reject the null in case of directional version. And the entire reason that's happening is because we have an effect which is much more significant in one direction. Okay, and that direction happens to be the direction that we are interested in. Okay, that's why it's also important when you think about the alternate, it's very important to think about what direction you're interested in. So our interest of direction was this, but what our non-directional version is also giving us is, is there an effect in different direction also? You're not able to reject at this level, but you're able to reject this at this level. So you're able to find out significance for your alternate in the second case, but not in the first case. Okay, and this was a subtle point. You don't have to focus on this, but just make sure you get the calculation of the p-values right. Okay, any questions? Does that answer your question? Let's see. Okay, cool. All right, any other questions? I know we are out of time as usual, but if there are any questions, I'm happy to take them. You're also welcome to stick around if you want to ask me questions. I'll stick around for next 5 minutes if you have any questions. But if not, that's it. Just make sure you don't forget to turn in your assignments and have a good spring break. Please stay safe. And I hope the problem soon dies down so that we can meet in person. But the week after spring break, again, we are going to do the same thing. So we're going to meet virtually. Okay, and hopefully this has worked out good for at least some of you. So I'll hope to see some of you back in the session the week after spring break. All right, that's it. Enjoy your spring break. Oh, okay. So next question, I'll answer it. Specifically asked. Sorry, this is supposed to go to Nick. Okay, that's fine. So let's do everyone. So if you're getting an error with the Wilcoxon test, it's actually not an error. It's actually a warning. And the reason the warning is happening is, let me share my screen again to give you an example of why that happens. Okay, so one of you asked this question about the Wilcoxon test giving an error. The Wilcoxon test giving an error in R. The reason that happens is you have in your data set examples which look like this. What do I mean by that? You have certain ties, like this is a tie. Now, if there is a tie in these two groups, then R just prints a warning that, I can't really figure out what this, how should I resolve this tie? So let me just warn you that the result might not be exact. So don't worry about it. That's just a warning. It's pretty much expected. Okay, for a QQ plot, how do we define? Oh, that's a very good question. Okay, very good question. Okay, so let me show you how to do that. And first I need to create, just give me a second. So the way to do that is to actually create, okay, this is not important. I mean, it is important in a real life, but it's not important. I'm not going to penalize you for this project, but this is what I expected you. And it's, in some sense, I actually did not emphasize this enough in class. but I'm going to show you how to do this in R. Okay, so this command is called QQLine. And I can show you once it shows up. Okay, hopefully you'll be able to see my R screen. Okay, so let's say you have this data, Cleveland HT. I'm going to use my console for now. So what's one way to plot is you do QQplot, Cleveland HT, and let's say BP. Okay, this is QQ. Okay, so hopefully, yeah. So you see a line here, and yeah, you're right. I can't really figure out whether this is a straight line or not. So I'm going to add one thing, and that's a very simple thing that I add. So which is QQ line. The moment I add a QQ line, you'll get a line, which essentially is a 45-degree line in some sense. And that will tell you whether this data is periodic, normal or not. So one thing that you can be kind of sure about is this data definitely does not look in some sense to be normal, because you see a lot of bumps here, and the upper extremes of it are deviating a lot from normality. Okay, and that's not normal. So let's do a quick check. I can simulate a random variable. Let's see how long. Okay, so 1 second. Keep using the wrong command. Okay. So what happens if you simulate a normal random variable? So if I simulate a normal random variable, which has, let's do this. Then by default, I see, in this case, the X value that I simulated actually is a truly normal random variable. And you'll see that it lies pretty much along the line. And this is what your null expectation should be if something is normal. Okay. And you can see that the line falls pretty much on this axis, which was not the case with the previous plot, because in the previous plot, it's going away from. So in some sense, it's actually violating the assumptions of normality. So if you're using, for example, a column, this was a BP column. If I'm using a BP column for doing t-test, the results are not going to be super trustworthy, but I can still do a Wilcoxon test on this. Okay, does that answer your question? Okay, it seems to be a straight line after 1 to 1. Okay, so that essentially means you have a lot of outliers in some sense. So if you have outliers, then that's going to be tricky. You can still do a t-test. It's fine, as long as there is at least one particular range in which the assumption of normality is satisfied. Okay. But just write this down, whatever you're observing, just write this down in your document so that you can explain what's really happening. Okay. Does that answer your question, Hari? Okay. Okay. Are there any other questions? Okay, if not, I'm going to hang up. Please feel free to email me and we can chat on Zoom if you have any questions about the homework or the project or the assignment or anything about the class. Okay, all right. Thank you, everyone. It was wonderful teaching it this way, and I hope you enjoyed it, at least to some extent. I'll have the notes available, and the recording will also be available in at least by I think by an hour or so. Okay, all right. Stay safe.